So let's look at continuous random variables now that we've done a lot of work with discrete ones and we've combined discrete random variables. Let's define a continuous random variable. So a random variable that can take any numeric value within a range of values is called a continuous random variable. So your range does not have to be infinite, okay, on both ends is what I mean to say. So it can be bounded at either or both ends. I often described discrete as ones that you can count. So if it's continuous, you wouldn't be able to count infinitely. Think about decimals, like all the decimals that exist between 1 and 5. You know, it could be 1.21, 1.211, 1.2111, so that being continuous. When we look at continuous random variables, all the rules that apply to discrete random variables also apply to continuous random variables. So the ones for combining we're going to still use. And we're also going to be revisiting the normal model. So some continuous random variables will follow normal models, but others may have a skewed, uniform, or bimodal shape. But regardless of the shape, all continuous random variables have means, which we now know we call the expected value and variances. So my second statement is when two continuous random variables have normal models, so does their sum or difference. So this is good because we are going to be combining like two different distributions. So let's illustrate with some examples. So the first one is that the heights of young women can be modeled by a normal distribution with a mean of 64 and a standard deviation of 2.7 inches. So suppose we chose a young woman at random and we let her height be capital Y in inches. And we're going to find the probability that her height then is between or equal to 68 to 70, and then we're going to interpret this value. So we've really done problems very similar to this before, but we are dealing with a random variable because we're randomly selecting a woman. So I'm going to remind you of good practice whenever dealing with the normal model. So first, you're going to sketch your normal model. So let's start by doing that. Do my unimodal bell-shaped curve here. Put my mean. And I'm going to do good practice of always labeling my parameters, that my mu is 64. Notice I'm using parameters, not statistics, because it's a model, and sigma is 2.7. And good practice is to label three standard deviations rather to the left and the right. So I'm going to add sigma on and subtract it from my mean. So next in our good practice would be, of course, to show our calculations. And there's really two ways I've taught you to do this. The first, I'll say method A, would be to standardize and then use table A, or you could use your TI calculator. And when I say standardize, that means you're finding a z-score. Or if you're totally doing complete graphing calculator talk, you really could have bypassed finding your z-scores. So let me show you good notation that you need for your AP exam would be capital P, the probability, you show what you're doing, that a woman, randomly selected woman, which was defined as capital Y, her height in inches, is between 68 and 70. This is equal to the probability that our z-score is between two corresponding values. So I'm going to find my z-score beneath this. I also labeled in my normal curve that I'm looking for that area between 68 and 70. So to find my z-score, remember, I take my x value, which is 68, I subtract my mean of 64, and I divide by my standard deviation, and I take it to 2 decimal places. I get 1.48. So my lower bound and my upper bound would be 70 minus 64 over 2.7 gives me 2.22 to 2 decimal places. So I want to find that area between 1.48 standard deviations and 2.2 standard deviations away from the mean. And now, just to remind you, I would encourage you to actually grab Table A so that you can get these areas. And remember that Table A is showing you the area to the left of the z-score. So I'm going to take the greater z-score of 2.22, and I see on my Table A that that corresponds to 0.9868 from the body of the table, and I subtract my lower, which was 0.9306, which gives me 0.0562 for my area. Now, it is acceptable on the AP exam to say that the probability between your random variables between 68 and 70 is equal to the probability that your z-score is between the corresponding values we just calculated. And rather than using Table A, you could say that this is equal to, and now you're using calculator talk, which is acceptable. Some will argue that it's not best practice, but it is accepted. And you label your lower bound, which is 1.48. Now you need to say that that's lower, or you won't get credit. 2.22 is your upper. Mu is 0 and sigma is 1 because we standardized. Notice that I just entered my z-scores. So go ahead, try that on your calculator, and you'll see you get 0.0562. I also want to remind you that this actually can be done without standardizing. Your calculator has the ability where you don't have to go to the standard normal. Now, bare minimum, you would still need to use proper notation where you're stating the probability that your random variable, the height of one randomly selected woman, is between 68 and 70, and you're bypassing all this work. But sometimes I argue that you conceptually don't always understand what's going on. I'm just going to move up a little bit here so you can see, is equal to using, I always state what I'm using on the AP exam, using TI-84, normal CDF. You're opening up your parentheses and you're going to label your lower 68, your upper 70. Mu is what it was in our model, which was 64, and our standard deviation was 2.7, again labeled. So I totally bypass all that hard work, and if you type that in, you'll also see you get 0.0562. And finally, regardless of which method you use, you absolutely need your conclusion in context. Okay, so I'm stating that the probability that a randomly selected young woman has a height between 68 and 70 inches is about 5.6%. Now we're going to look at some continuous random variables where we're combining them. So it says a company manufactures small stereo systems. The packing stage can be described by a normal model with a mean of 9 minutes and a standard deviation of 1.5 minutes. The boxing stage can be modeled as normal with a mean of 6 minutes and a standard deviation of 1 minute. So first we're going to look at what is the probability that packing two consecutive systems takes over 20 minutes. So I'm going to define some random variables first of all. So I've got a packing stage where I'm given mean and standard deviation, and then it talks about the boxing stage and its mean and its standard deviation. So I'm going to say capital P is the time to pack and B is the time to box these stereo systems. So what is the probability that packing two systems take over 20 minutes? So I'm going to say P sub 1 is the time for packing my first package. And I'm going to say P sub 2 is the time for packing the second package or stereo. Okay. And I realize I'm going to be packing 2 consecutive ones, so I'm going to be adding these together. So rather than repeatedly writing P1 plus P2, I'm going to define a third variable, and I'm going to say T is equal to P1 plus P2. Now, we're going to check 2 conditions, and this is going to be something that we start repeatedly doing throughout the second part of this AP course. In order to use a normal model, we need to confirm that our data are normal. Well, we are told that our data comes from the normal model or follows a normal model, so it's safe to conclude that. And the next thing that we have to do is we've got to check for independence. And why do we have to do this? Well, we learned before that in order to combine our standard deviations, you can only do that if we have independence. So our independence assumption, we can assume 2 packing times are independent. All right, so now that we've checked both of these conditions or assumptions, let's go on to our calculations. And I'll tell you, sometimes it seems tedious to bypass that, but if you do, you will lose credit on the AP exam, or even get no credit because you're doing something illegal, because you would not be able to combine your standard deviations if you did not have independence. All right, so we have both stages can be described by a normal model, but we are packing 2 consecutive ones. So we're going to be developing a new normal model here. So mu of my total is the same as my expected value. We know we call it expected value with random variables. And what are we going to do? We're going to add our 2 means together. Well, it's going to be 9 plus 9 because we're packing 2 consecutive ones. So our new mean or expected time would be 18 minutes, but we're going to always have some variation with that. We always do, and we need to work off of our variance. We can't just add our standard deviation. So what are we going to do? Well, I have it highlighted in red. It's 1.5. I square it for the variance plus 1.5 squared. Let's see, put that in my calculator. And I get that it's approximately 2.12 minutes. So, you're combining 2 random variables. You would expect for your standard deviation to increase. So I'm going to sketch my normal model now. I just zoomed out to give myself a little more space. Not a bad idea to state what this is. And now what are we calculating? We are asked what is the probability that our total time takes over, and we said our total time is t, is over 20 minutes. So I write the probability that t is greater than 20. Now, so I can standardize and use table A, or I can just jump right in using my calculator talk. And since it took so much to set up, I'm going to jump right in here and say normal CDF, and this is equal to my lower is equal to 20, upper is equal to 999, mu is 18, and sigma is 2.12, and that produces 0.1727. So I'm going to state a conclusion in context, but I will say, you know what, I totally forgot to label what this looks like in my picture. So 1 standard deviation away would have been 20.12, and it's just a good idea to always draw it in to see that your area makes sense. So we're getting like a 17%, which is making sense. If you got something like an answer like 95%, you can see that your area is clearly not that, which is why that picture is so huge. So my conclusion in context is that there is little more than 17% chance that it will take over 20 minutes to pack 2 consecutive systems. So let's expand on this same scenario. So it says, what percentage of the stereo systems take longer to pack than to box? And I also already stated that I would use capital P to represent the time to pack a stereo and capital B to represent the time to box a stereo. So if I want to know what percentage of the stereo systems take longer to pack than to box, if I think about that, that means if I'm subtracting the boxing time from the packing time, I want that difference to be positive. Okay, so I want this difference to be greater than 0. So it might again be easier to say, to define another variable where I say D is equal to P minus B, which would be my difference in times. So what I'm really looking for then is what's the probability that my difference is greater than 0. So if I am finding the difference of two random variables, I'm going to need to check my assumptions, and I'm just going to say that I did this, it's the same as part A. All right, so I'm not going to redo this. I've checked that for normality, my data, they follow a normal model, and I checked for independence so that I can combine my standard deviation, okay? So I'm not skipping it, I'm just saying I already did it. Now, what is my new mu? So the mu of my difference, okay, so that would be 9 minus 6, and that is my new expected time would be 3 minutes, the average of my expected times, and my standard deviation of P minus B. Now, why did I write it this way? Because I thought it would be easier for you to remember that my standard deviations will not decrease. It's going to increase. This is the same as P plus B. So I work off of my variance. So it's the square root of 1.5 squared plus 1 squared, and that's going to equal approximately 1.80 minutes. So what am I looking for? Well, I want to know the probability again that D is, and I really wanted that to be the probability that D is greater than 0. That needs to be in parentheses, and I just noticed up above that I did the same thing. So let me just erase this right here and say the probability that D is greater than 0. That's my event in parentheses. Okay, and what's that equal to? Well, in order to see that, I'm going to make a normal model of the difference in my packing minus my boxing. So my mean normal model is 3, and my standard deviation is 1.80. So I'm going to take a second and label my normal model. So I've labeled some of my 1 standard deviation, 2 standard deviations, and 3 standard deviations to the left of the mean. And I just want to point out that this does not mean it takes a negative time to box, but if I got a negative, this would actually mean that it took longer to box than to pack, okay? That would, when I subtract the two. So I'm looking for the probability that the difference is greater than 0. So 0 is going to be about in here, and then I'm looking for this area in here. So if standardizing is your go-to route, this is equal to the probability that your z-score is greater than, off on the side to find my z, I would do 0 minus 3 over 1.8, and that's negative 1.67. So the probability is greater than negative 1.67 standard deviations, so not quite 2 standard deviations below the mean is what that's saying. And this is equal to, I'm going to do a little calculator talk, which is equal to 0.9522. Okay, so you could also do it by table A. You could also use the standard normal using the calculator. So you would just use your z-score, negative 1.67 for your lower, 999 for your upper, 0 for sigma for mu, and 1 for sigma, because your standard normal is always 0 and 1. And then you just write your conclusion in context. So we would say about 95% of the stereos take longer to pack than to box.